I'm gonna backflip our slides. I'm gonna start with our last slide, which is the thank you slide. I came here for first time last year, and the whole thing that we started here, it was from last year. So, but before I go there, let me introduce ourselves. I'm Bill Pontikakis, and he's Francois-Raymond. And he's a professor at Polytechnique, because another thing, we forgot to put our affiliation on our slide. So he's from Polytechnique, Montreal, and I used to be the research associate for the NSERC Canadian Industrial Researcher in Programmable Networks. And we had 3 industrial partners we had back from the beginning. One was Intel, and we had 2 Montreal local companies, but unfortunately they filed bankruptcy. And so we're doing this for the last 4 years. The chair was for 5 years, but I came on the 2nd year. And we had to do a lot of different research, but all of them were concentrated to the P4 and programmable networks. So we came here last year, and I'd like to thank you, because this is an amazing community, a fantastic community, actually. And I met a lot of cool people, and with some of them are here again. And I had some great talk, and Mirek is here that after the last year P4 workshop, we met at the old Aters buildings with some Star Wars team, playing around with each other, and say, okay, I have this idea, okay. And that's the idea came out. The idea was to have a front haul ECPRE that's already existing, like in hardware. How can I take this into P4 language? Can you do anything about it? And back then, I didn't know what was ECPRE. I had to ask Mirek. He explained to me this, okay, go now, fetch some information at the Intel side and find your way around. And that's what we started with. And I'll go down to the conclusion and continue doing this. But at some point, I'm going to sit at the beginning. So what we end up with having is, at the end, we have to test what we had, and therefore we had to use the PTP-1588 time synchronization protocol. And we had to do some kind of implementation in the BMv2 switch, because that was where we want to test it before going to hardware. And unfortunately, the current implementation of timestamps in BMv2 cannot accommodate what we need as a precision. So we need to modify that. So we did a modification, and our timestamp is more versatile and makes the BMv2 a little bit more future-proof. So I continue going back a little bit. So now our claim is that with the current implementation of the timestamps in BMv2 and ours, we have a big difference. It's how from microseconds, we made an improvement, basically, from microseconds to nanoseconds. And then you're going to tell me, Bill, that's a big claim. I don't believe you. Can you prove that?
I don't believe
Yeah, I know. So now I'm going to go to the beginning.
Don't show the graphs.
The BMv2.
No.
Not now. I'm not going to go to the graphs now. So that's what we try to do. We try to, this is our thing. We propose a new ingress and egress timestamping in BMv2 to support any kind of a timing synchronization, but in our case with the PTP-1588. And in the agenda, I'm not going to go through this too long. I have the why, the how, and the what. Oops. Basically, why we did what we do with the PTP, which was the ECPRE I told you, and how we do the implementations, and what results we had. We had to do some error resolution from existing design. I'm going to show you some results. So I'm going to go to give you some context so we don't have any hallucinations. So initially, or the older days, we have these legacy cell towers, and we have the cell site cabinets. And the communication between the two were through cables that are coaxial, copper, very slow. They were power-hungry antennas because of the amplifiers. And on the cabinet was collocated the baseband unit and the radio units. And it was very low bandwidth. It was not good for scalability as the mobile networks were evolving. So the next idea is to make the RU, the radio head, collocated with the antenna. Now they replace the coaxial with a fiber, and we have now the baseband unit on its own. However, this design was, and the communication now was this through the front haul proprietary, the called proprietary front haul protocol was the CPRE. And the CPRE is basically means it's a protocol for the interface, basically, for the radio interface, the common public interface protocol. So now, because the solution was proprietary, and even though it was better for the run, people were coming with a new idea. The new idea was the operand. And in the new idea, now we have 3 main units: the radio unit, the distribution unit, and the core unit, and the centralized unit, actually. And the radio unit now is integrating the antenna. And now the communication between the radio unit and the distributed unit, it happens through the enhanced CPRE. which is kind of an open interface. And this has the ability now to support kind of vendors like, because now the interface is more standardized, you can have some vendor neutral implementations, but at least in theory, I'm not going to go into details what I say, at least in theory, because some people have some concerns about this. And there are benefits because of that. And I have cost savings, you have more innovation, and basically we said to ourselves, and before I go that, I'm going to take you a little bit far away and say, if I go to a high level end-to-end network architecture, where are we locating with our design? Lately, the last year or two, we've seen some people taking the ideas from P4 and implementing with more in the edge data center, in the middle thing, where is the UPF, and they have done some designs of P4 in UPF. But we more into the left of these slides with the RUs, the ready units, and the data center there. And we try to make this front-haul connection now using P4, because there already exist implementations. And that router you're going to see there, let's go next. And I'm going to use some Intel, because the idea came from there. And you see there is the ECP there with the timing protocol. In the ECP specification, the timing protocol comes in the synchronization plane in the red line. We didn't use this approach. I'm going to tell you next slide our approach. And basically, now the ECP is used to transfer, to use the router there. It's actually a cell site router. That's what it is. And we're going to use that in order to aggregate information coming from the ready unit. So now the ECP is susceptible to delays and packet loss, special congestion. And the 5G protocol is very strict into time requirements. Therefore, PTP is used there to maintain some precise synchronization, do some correction in phase errors in the clock and stuff like that. So to continue again with Intel, another Intel diagram here. And since I was told to go fetch that information to start from somewhere, we use this as a starting point, but we didn't know the internals. I just used the diagram of it to get an idea of what I want to implement in P4. And we started with the most important part to me, and also the harder part, which it has, to me, different applications, not only for this one, the concatenation and deconcatenation part of the packets. And that's where we started, and we spent some time there. And then we start moving towards the left. We didn't do the right part, the pink part, because that has to be backwards compatible with the CPRI, and we didn't do that part. And as we move forward, at one point, my student says there, oh, so we're done. I said, no, now we need to test it. I need to do something about the TOD, the time of day management unit. So we have to come with our way of implementing something to test our design. And I'm not going to show you anything about ECP because that's going to be another set of slides in P4. And we did create a modular version of it because we had a lot of repetitive code. And I'm not going to do that either because that's going to be another set of slides. And we haven't published anything about all this, by the way. And just we're going to concentrate on this talk on how we did a PTP-1588 over IEEE 803.3 implementation in P4. And to do that, of course, we had to modify the BMv2 switch. So our thing is not full PTP implementation, it's just a proof of concept. So am I missing some specifics of the PTP specification, of course, but it fits what we need to do. And because we're going to get out of time here, I have to start moving. So with all the timestamps, as I said before, they lack precision, and I'm going to show you next slide why that's lacking precision. It's because of the way they're placed in the pipeline. And in the way we did it, maybe I should go already so I can. It's the most important slide of the presentation, actually. So as you can see in this slide, and I can see better here, we try to put as early as possible and as late as possible to place our timestamps in this pipeline. And as you see before, they were either in the simple switch ingress code, which is not exactly as early as possible. And on the other side, it was there, and this traffic manager doesn't really exist in BMv2. There's some kind of a buffer, I think, there in BMv2, and that's where the timestamp currently exists. And we said, no, that's, and I don't say this is not good, like it has its own advantage, right? If you want to see how long, for example, the packets are staying there. But for our case, it didn't fit our thing. So we tried to do outside as much as possible to write on the BMI port. And that's what we did. And I'm going to show you how we did that now. And I'm going to allow Francois to take over for this part.
Yeah. So the main calculation that is done is in PTP, which has to be precise, is the time between the output of a packet and the reception of that packet. And if that time is between the here the egress and the simple switch on the other side, there's plenty of space here that could have a big variance of time, and we will not have an accurate time. So we want to remove that, and that's why we try to have the timestamps really at the end and at the out and the input. Now we will have to modify the BMI code, and we will have to include some more precise timestamp because current timestamps are like in microseconds. We need nanoseconds accuracy, so we use better timestamping, and we need to have an absolute timestamp. So we use the kind of Unix timestamp with it starts on January 1970. And we have the second part, which is 32 bits, and the nanosecond part, which is also 32-bit to make 64-bit. We have not implemented the full 80-bit of PTP that can support, but it's enough 64-bit for most applications. And to integrate that into BMI port, the problem is that BMI port is like the only part almost of the behavioral model, which is programmed in C. So we moved it to C++. Maybe that the course that I teach the most currently is C++ may have an influence on that also. But we had to, we thought that moving to C++ would be a good thing. And to have more expandability, we used some structures instead of current how the parameters are passed. So we can, in the future, extend to have other like metadata that could be passed from the input part to the switch. And we wanted, of course, to test this new port. For the egress timestamp, we will have also to like remove some of the possibilities that could be done from inserting it in the P4 code, because we are moving it to like a fixed end, but it improved precision, and it's still working with multiple protocols. We are not fixed to PTP. So to do that, we added 1 bit for enabling the insertion of the timestamp in the egress, and an offset so that it can support other protocols than PTP. So here, the P4 program calculates the number of bytes here to tell where we should inject the timestamp at the output. Now, how we do that? For the input part, we need to change how the function which registers the packet handler is done. Currently, there's a function that takes a port and a buffer, and unless we try to hack the pointer of the buffer or the cookie, we cannot pass any other metadata. So instead, we added a struct where we have metadata here, and it's easy. Anybody can add some fields that metadata pass other data to that packet handler function. To register that packet handler, there is here a function where we call the old set packet handler. We kept the old one and we added a new one. Why we kept the old one is because we know that most people use BMv2 to do some testing and have probably their own version modified BMv2, and we want to not break the current code of everybody. So as we had to change eventually the base class, we want that if you have a derived class, it's still working with the current base class. So standard current switch will work with a new port or with an old port, and there's no problem. There's another problem with the BMI port code. It's not just that it's C code, it's that it's not tested. You can inject some errors in your BMI code here and test that all the tests of BMv2 and P4C compiler passes, even if you put a big error in that code. So it's just not tested because the current injection of packets to test simple switch is through nano messages injected directly to simple switch. To be able to test the BMI port, we added a libpcap mock that we replace at compile time to replace the libpcap that is used by the current BMI code. With that, we found that there was bugs in the current BMI port. So the destruction of ports destroyed only half of the ports because the loop was incorrectly made. And the BMI port interface removed had a possible deadlock because it was holding a lock while waiting for something. And the dev manager BMI had a race condition where while the BMI dev manager was destroyed, there was a thread that was running which could call a method from the derived class when the derived class was already destroyed. So you need to stop the thread in the derived class, not in the base class, which was causing two problems. Now that we corrected those problems, we have this environment where we have a Python code that put packets in our P4 switch. We have another P4 switch. We have here the PTP conversation to have either 3 or 4 messages to exchange and have our correct timing measurement. Want to do the
Go ahead.
Go ahead. So the timing measurements, this is the timing with standard. If we try to implement it with the standard current BMv2, first we have to use the 4 packets, not the 3 packet version, because we cannot implement the 3 packets without modifying BMv2. And we see here that we have a lot of variance. The variance is, well, the standard deviation is like 13,000. The range is 73 milliseconds. Okay, but if we look just at the 90th percentile, we have like 24 millisecond range. If instead of that, we use our modified version, we see here the peak, which is much more narrow. We have 0.05 millisecond max and 0.05 minus 0.05, so only 19 microseconds instead of some milliseconds. And here, if we take the 90th percentile, we have like 9 microseconds. So this is.
And we hope now you believe us, and we also have a demonstration to believe us even more. And thank you again. Let's go back to the thank you slide.
Yeah.
This looks like really good work. Whenever I'm kind of puzzled because it seems there are, some sources of real, sort of high jitter in this system, like, Python and like BMv2, I mean, a nanosecond, how many packets can BMv2 crank out in a nanosecond? Not that many, right? So I don't quite, I mean, I think this is good. Like reducing the jitter and variance, I think is a really good idea. My question, I guess, is how do you compensate for these other sources of variance, like Python, VMv, and low performance BMv2, things like cache misses, TLB misses, page faults? Linux finally has, real time, and the kernel are using real time. Like, how can you further address these other things that can really introduce huge jitter and variance?
Well, in the PTP protocol, all the other variants are not important. It's just the place where you output a packet and you get it. So Python is not in the path here. We have the output of BMv2 going to Mininet, going to the input of BMv2. Of course, there are cache miss. Of course, there are context switch that can really mess this up. In fact, when our student was doing the test, while we were looking at it, the tests were much worse because we were currently using like Teams with video, which was on the same computer that was running also the test. So if we really want to have that variance really shorter, we would have to like use maybe a real-time thread that does the synchronization. We did not, well, I did some testing just setting the process to be real time. It improves it a little bit. This is not even with real time. It's just a standard process.
And we had some other problems that you remember with the threads.
Yeah.
I guess my thought is that I'm having trouble understanding the idea of measuring something with such huge variance and error at an extremely, at a, precision granularity that's, far below the noise floor, right?
Sorry, since you have a demo, I encourage.
Yeah, you have a
to
demo.
follow up with more detailed questions.
yeah.
There, thank you
Yeah,
very
yeah,
much.
no,
for
we
your
don't have
help.
time.
Yeah, yeah.
Okay,
Thank you.
Thank you.